I have this dashboard to build, and I need to provide this dashboard real-time update. Um, and with REST API, it's not very handy because I need to implement long polling to request my API every few seconds to update the dashboard, so it's not really handy. And a colleague of mine, actually, Brandon Minnick, maybe you know him. Brandon Minnick delivered a lot of talk around async with patterns, and he's one of the guy of the .NET MAUI community toolkit. Brandon told me, hey, Francois, for your use case, you should take a look at GraphQL because you can get on the client side some real-time update of what's happening at your data on the server side. So this is where this talk started, because at that time I was like, okay, maybe it's time for me to take a step back and look at what are the backend API technology I can use in .NET to build my backend, and not always go to the default of building a ASP.NET Web API. So today it's an introduction talk. It's for, I would say, beginners, because sometimes we miss beginner content. So I want to share with you what I've learned, and at the end of this presentation, I will share with you my decision tree to pick between one of them. So it's a very opinionated decision tree. It's my decision tree. It's not AWS endorsed decision tree. You may disagree with it. That's fine. Let's discuss this as everything. And of course, you will find some use case where my decision tree is not appropriate for your use case. So always assess regarding to your requirements. So just a bit of me before going further. So as I've told you, I'm a .NET developer for the past 20 years roughly. I work at AWS as a Microsoft Specialist Solution Architect, so I help AWS customers to use .NET on AWS or other Microsoft technologies. I worked at Microsoft in the past. I've built a .NET application for on-premise data center, for Azure, and for AWS, so I have quite some experience on this. So that's my background. Okay. So in terms of backend technology and on purpose, today I will focus on this for backend technology: REST API, gRPC API, GraphQL API, and SignalR API. You can use other technology like OData, for example, but I will focus on these four main ones. I would say with those backend technology, you can already cover a lot of things, but as always, you can find more suited technologies for your use case. For example, on the IoT side, you may want to look other technology. So those four technologies are most of their implementation, and I want really to use implementation, relies on HTTP or HTTP2 or WebSocket or server-side event when there are two-way communication. So those technologies are implementing on top of those protocol. And we'll see we will go in deep, not in deep, but we will go through those four technology for .NET developers in the rest of the presentation. So let's start with REST. And personally, I thought REST rules the .NET Backend API world. Who is agree with that? Or who thinks that .NET ASP REST API rules the .NET Backend API world? Yes, a lot of hands. My answer is no. The reality is no, and it doesn't matter, and I will explain why. There is a trick there. So let's go back to the root. And the root of REST is the PhD thesis from Roy Thomas Fielding back in 2000. So there is a QR code here to direct link to his thesis. his dissertation. And don't be afraid, I went through it, and it is human readable. You don't need a PhD thesis to read this thesis. And this is the source of truth about REST. And when I was reading his dissertation, I realized that the content you can find on the internet about REST is, for the best, incomplete, or in the worst case, totally wrong. So let's discuss what REST is. So first of all, REST is an architectural style. It's not a framework, it's not a specification, it's an architectural style defined by Mr. Fielding. REST stands for representational state transfer. Sorry for my French accent. Some words are very difficult to me. So it is a resource-oriented architectural style. It means that what you transfer between your different compute nodes is the representation of the actual state of your resource or the desired state of your resource. So you are not transferring an action. You're not saying, I'm doing this action on your resource. You're really transferring the representation of your resource. And Mr. Fielding defined REST with 6 constraints. The first one is very heavy. It is the client-server constraint. So it means that you have 2 compute nodes. One is acting as the client. It defines the request and sends the request to the other compute node, and the second compute node acts as the server. It processes the request and sends back an answer. Pretty easy. Most of the internet is built on this paradigm nowadays. You can find distributed system, but the main system is client-server. The second constraint is stateless interaction. It means that your server doesn't need to know about the state of your client to process the request. Everything needs to be in the request message to be able to process the request. The third constraint is cache. The system needs to define explicitly if the answer is cacheable or not. The fourth constraint, I will come back to this one later because it's a very important constraint. It is the uniform interface constraint. The fifth one is layered system. It means that if you have 3 compute nodes, A, B, C, the compute node B can be the server for compute node A and the client for compute node C. So if compute node A sends a request to compute node B, and compute node B needs to send a request to compute node C to bake his answer to A should not be aware of this. Actually, it must not be aware of the existence of compute node C. It's a layered system. And the last constraint is code on demand. It means it's the only optional constraint in the 6th constraint, and it means that the client can download some code from the server to execute locally. So back in the day, it was actually for the Java applet. Nowadays, you can think of this like when you download your single-page application bundle that will run inside your browser. So this is this kind of constraint. And let's now take a closer look at the uniform interface constraint. So this constraint is, in fact, might seem quite simple, but it says that you need to have, for identification of resources, you need to have a unique identifier for your resources. So each resource on the back end must be identified by one unique identifier. You manipulate your resources through their representation. I've already mentioned this. The messages are self-descriptive. That it means it helps with the fact that you don't need to know, the server don't need to know about the client to process the request. And finally, this is the last part of this constraint. The hypermedia as the engine of application state. I won't try to pronounce this acronym because I don't know how to pronounce it. So what does it mean? Let's take a look at a movie catalog API. So you send a request to your catalog to get the detail about a movie. In the answer, you will get the title of the movie, you will get the description, and you will get the list of actors and actresses of the movie, in the movie. And if the system gives you the ability to request more detail about one actor or one actress, it will provide you an hyperlink in the answer so that you can directly use this hyperlink to get the details about the actor or actresses. You don't need to know, your client application don't need to know about how to build this hyperlink. It's in the answer. So, and this constraint is not optional. It is mandatory in Roy Fielding dissertation. So now, what is a REST API? It's any API that implements REST constraint, whatever the protocol and component implementation. Because in his dissertation, it doesn't mention that REST should be implemented or on HTTP, or you can try to implement those constraints with SMTP. Actually, it has been tried in the past. But HTTP 1.0 and 1.1 development has been used to validate REST architectural style. Mr. Fielden was part of the working group on those protocol, and HTTP 1.1 is built, or at that time has been built, to be the ideal protocol to follow REST principle and constraints. So at that time. So in practice, most REST API don't implement the 8 OS constraints. So most REST API are not REST API, and that's okay. So we should be very accurate on this. Implementing this constraint can be worse in some cases, but it's not trivial. With Spring in the Java world, there is a Spring HOS libraries. We don't have this kind of libraries in .NET. And actually, it has been a hot debate. And in 2008 at KubeCon, Leonard Richardson has introduced the REST API maturity model. So level 0, you have only one unique resource identifier and one HTTP method. So you are really at the level 0 of the REST API maturity model. Then you have many unique resource identifiers. So each resource is really uniquely identified on the backend, but you use only one HTTP method, like get. You use get for everything. Level 2, you have many unique resource identifiers, and you use multiple HTTP verbs to manipulate your resources. You use get to retrieve, to query the resource. You may use put or post, and I won't go into the debate of whether you want to use post, put, or no. You use multiple HTTP verbs to manipulate your resources depending on what you want to achieve. And finally, level 3 is the GRAR. You implement all REST constraints, and then you are a REST API. Actually, if you use ASP.NET Core Web API, you can say that you are at level 2 by design. When you build ASP.NET Core Web API, you are at level 2. So there are some challenges with REST-like API. Performance is in microservice architecture. This is one topic where people try to look at other backend API technologies. Data flexibility, because when you are using a REST API, you have a schema. It is a fixed schema, and if there are some properties you are not interested in, you get them. Two-way communications. REST is really, okay, I send a request to my server, the server answers to me. That's it. And also nowadays, streaming request and streaming response is a hot topic in many domains, so it's not designed for this. So what about microservices? What I know, I'm not a microservices expert, so sorry if I say something wrong. But what I know about microservices is that they should own their domain data. I can read this a lot. They should own their domain data. So we can ask the question, if they should own their domain data, does it make sense to transfer the resource state, to expose the state of the resource to outside the microservice? So in this case, remote procedure code is a valid approach. And gRPC is a good framework to work with this. So Google and others have been designing gRPC for years. They have a set of design principles and motivation. I won't go into the details of all those design principles and motivation. You can find them on their blog. To me, an important thing with gRPC is its portability, its interoperability, because you can find implementation of gRPC in 11 different programming languages, and it guarantees you that if you build, let's say, like in this situation, you build a gRPC server in C++, and with the same service definition, you build a Ruby client and an Android Java client, you are guaranteed that it will work. It will be interoperable. So that's pretty cool. And it uses a binary format for a message exchange, so it's it's performant. It reduces the overhead. So how does it work? Here you have a Ruby client, for example. You have inside your application a gRPC stub. It will send a proto request to your gRPC server, and the gRPC server will send back the proto response. And you can do the same thing with another application written in Java, for example. So what is the anatomy of a protocol buffer service definition? So let's say I have a movie review service. So in my situation here, my service will expose. Okay, give me a second. I'm looking for my. Okay. Here, my movie review expose a procedure called add review, and my procedure take here a review request message as an argument, and send back a review reply. And in my protocol buffer service definition, I define the shape of my review request message and my review reply message, and that's pretty easy. And then I can use this protocol buffer service definition to generate the stub of my client code app or my server code, and then I just have to implement the business logic. And the framework, the tooling, take care of the plumbing for me in most cases. So that's pretty cool. And you have the implementation for C# and .NET, of course. The benefit of using gRPC. So generate the client and server code in 11 languages. I hope they didn't had a new language in the past months. They leverage HTTP2 performance improvements. So by design, it has been built for HTTP2, not HTTP1 or 1.1. So it really leverages HTTP2 performance improvement. It supports bidirectional streaming. It means that your client can open a connection with the server and send message into this connection and stream message to this connection. And same for the server can stream responses to the client and keep the connection alive. And you can do both at the same time. So the client can stream request, and while the client is streaming request, the server, while it processes the request, can stream responses. And there is an extension APIs to plug authentication, tracing, load balancing, and health checking, so it's quite extensible. So you can use gRPC in such a situation. But now, let's consider another challenge. You have one API and multiple consumers. You may have the website where you can display a lot of information. You may have the mobile application where you want to display only a subset of the information. So you have multiple representation depending on where you display the data. And then we fall into the one-size-fits-all issue with a REST-like API. You may try to optimize for reducing the number of requests. And in that situation, you will have heavy messages to serve all clients because you try to, not forget one property, but you will have irrelevant data for most clients, and you will have impact on bandwidth if you are, for example, building an API that will be used over a mobile network, for example. Don't forget that 5G or 4G is not deployed everywhere, so you may think about the bandwidth. You may also optimize for transferring only what clients need. And in this case, you will end up with small messages with little information, and to send multiple requests to get all the required data. And that's exactly the issue Facebook experienced back in the day with the Facebook, the very first version of Facebook on iPhone. The application was really lagging, and they tried to figure out why, and they realized that they were sending a lot of requests because when you were in your feed to display your feed, they were sending a lot of requests to retrieve multiple type different data, and it had an impact on the bandwidth. And this is exactly why they've started to design GraphQL. So it's a query language that allows you to send a request, a query where you can define what data you need. And I'll come back to this later, but really to shape and say, hey, I want this piece of information, I want the movie, but don't give me all the information about the movie. Here I'm on the mobile application, and in the feed I will only display the title. So send me only the title of the movie. Don't send me the rest of the data. Or if you are on the web application, for example, then you can send different requests, but to the same API saying, hey, send me the title, the description, and the list of actors and actresses, because I have much more space to add information. So it comes with a query language and a server-side runtime for executing the queries. It is database or storage agnostic. The specification is also agnostic from transport protocol. In practice, most implementation rely on HTTP and JSON. Here again, I've seen some folks trying to implement this on SMTP. I don't know why, but with their implementation, you can send an email with a GraphQL query, and the email server replies with the data. So it works. So Here is a very simple definition of a GraphQL API here. I define my query, so I specify my type query. And here I could have a list of different query I offer, my API offer. So here I have a movie query that takes an ID as an argument and return a movie object. And then I define my type movie with an ID, title, description, and a list of actor, and the type actor with the first name and last name. Then I will craft my query. So here, this is the shape of my query. I say I want the movie with ID 1, and I just want the title. So please send me back the information. And then the server will return the movie here, Return of the Jedi. So that's it. That's very simple. That's not as simple as this, because behind the scene, you need to provide also a resolver to your server-side engine to let your server-side engine know how to actually query the data, where it needs to retrieve the data on the backend. So the benefits of using GraphQL API, you query only the data the client needs. One use case I've seen a lot in France, I don't know for other countries, it's to proxy multiple legacy data systems in one API. For French banks, I've seen this a lot. They have multiple legacy systems, but they had to catch up with fintech. They had to build nice mobile application, very modern application. So what they did is to build GraphQL API, and on the back end, the server-side engine was querying their legacy system, gathering the data and sending back the data in one nice answer to the mobile application. So this is the kind of system of use case you can cover with this. The challenge of GraphQL is the learning curve. It's a language, so as any language, there is a learning curve. The other language is caching. Of course, obviously, if all the query are different, it makes it, and all, by the way, all the answers are different, it makes it harder to cache the answer because they are different. So there are some techniques. I won't go into the detail, but it's quite tricky. Now let's see a real-time data update. So what is the need? The client, the standard HTTP flow, the client sends a request and the server responds, and that's it. But what if a data update occurs on the backend, and you want to be aware on the client side? That was exactly my use case for my dashboard. I want to display the dashboard, and I want to be notified that, okay, the data has changed on the backend. So you like the server to send notification to your clients. So you have a first option in the .NET space, which is quite well known and popular. It's SignalR. It's an open source library provided by Microsoft. It implements server to client remote procedure calls. So from the server side, you can query you can call some procedures that are stored in your client code. And the framework automatically, in that case, it is a framework. The framework automatically chooses between WebSocket, server-sent events, and long polling, depending on your browser capabilities. So if you are running on all browsers, the framework will select for you the best technology to use. A few caveats with SignalR. SignalR is strongly tied to the .NET ecosystem. So if you work in a company like me, I work at AWS, and this is not a .NET shop at all. So it's a bit hard to sell SignalR to other teams. So they look at you, well, what is this? So if you work in a company where .NET is not I would say, the main development stack, you have to deal with other teams, Java development team, JavaScript development team. Of course, there are JavaScript, .NET, and Java client, but if you go and speak with your JavaScript development team or Java development team, you will quickly discover that they are not likely to use SignalR. And for the backend, there is only a .NET Server implementation. Another option is to use, then again, GraphQL. Over the year, they have added other operation than only the query operation. Of course, you have the mutation operation to change the data on the backend. So with the mutation operation, you can here, let's say, movie-like mutation. So you want to allow your user to +1 on the movie in your catalog. The important part is that it comes with another operation called subscription. And here I have a movie-like subscription operation. And what it gives you. So I have clients B and C. They request a subscription to movie-like subscription operation. It opens a connection between them and the server, and this connection is kept alive. And then client A send a request for a mutation on the data, movie-like mutation. And when the server processes the mutation, it knows that it needs to send an update to client B and client C to let them know that the data has been mutated. So most implementation on GraphQL side use WebSocket. So you have to assess if you're in your use case, WebSocket is a good protocol. If you want to support very old web browser, you may have an issue with this, but nowadays most modern web browser implement WebSocket. So here it comes my decision tree. So I start with the question, are you building internal service-to-service API? If yes, the next question you should ask is, can you easily coordinate service update? Because as I told you, gRPC use a binary format messages, and sometimes when you change the procedure signature in your service definition or the message signature, it can break the compatibility. So in that case, you need to update the client or the server at the same time. Of course, you can also decide to handle multiple versions of your service at the same time to support older clients. But if you update frequently your server definition, you can quickly go into a mess having multiple versions of your service running in parallel. So if you can easily coordinate service updates and in a microservice architecture, it's in general, you work mainly with internal teams that support other microservices of your organization. You can easily coordinate. So in that case, you can use gRPC. If you answer no to one of those questions, then I would go, okay, is your need to have a two-way communication? If yes, next question would be, do you need clients or bidirectional streaming capabilities? If you need streaming capabilities, same question, can you easily coordinate service update? If yes, use gRPC. If you can't easily coordinate here, I would say maybe reconsider your design because you will go into trouble. If you don't need bidirectional streaming capabilities or client streaming capabilities, then you can use a GraphQL subscription or SignalR. If you don't need two-way communication, my next question would be, okay, do you need to support multiple clients with different needs in terms of data? If so, I would then maybe recommend to take a look at GraphQL API. And of course, most of the time you will work jointly with GraphQL subscription and GraphQL API. If you don't need to, you don't have this need of multiple clients with different needs. My last question will be, do you need to optimize for bandwidth because you are in a very constrained on a very constrained network? If yes, go to GraphQL API. If no, you can build a REST-like API. And if you look at my decision tree, the left part is mainly for inter-service API. In the middle, you have real-time, let's say, near real-time API. And on the right, what we call web API. My assumption is that most of the time, I would say in 80% of the case, you will end up building a REST-like API because it's simple, it's easy to build, and it covers most of the use case you will have. But on the other end, for other use cases, think about gRPC, think about GraphQL. And once again, this decision tree is for beginners and does not imply that an alternative architecture is wrong. Okay, you may be in a case where it fits the need of your company, the need of your use case. You always have to assess. It's really just a mental model to avoid the go to default REST-like API. So that's it for today. Thank you. So we have time for questions if you have.